This is 9.1, day 2. In the last notes, we talked about hypotheses, like a null hypothesis or an alternative hypothesis. In these notes, we're going to talk about p-values. So I'm glad that our classes have had a lot of experience with simulations so far this year, because that means we've already had experience with these p-values, and you'll see what I mean by the time we're done with these notes. So let's start off with, what is a p-value? Well, that capital P in p-value just stands for probability. So you can just call it probability value if you want. And as statisticians, when we talk about probability here, we want to know how rare our data really is. So one way to think about it is, like, what's the probability of our sample actually occurring just by random chance if that null hypothesis is true? So if that original claim, whoever made it, the null hypothesis, if that's actually true, how rare would it be to get our sample data? So that's really what it comes down to. Let's put that a little bit more formally. We could say a p-value is the probability of getting a statistic, or some people just call that a sample statistic, like x bar or p hat, for example. So it's the probability of getting a statistic at least as extreme as the one observed, basically the one we see in our data, under the circumstances that the null hypothesis is true. So if we're making the assumption that the null hypothesis is actually true, how rare is it that we would get this sample data, whether it's sample mean, x bar, or sample proportion, p hat. Or like we saw in the golf example, it could be sample standard deviation. For the most part, we're just going to stick to sample means and sample proportions, though. So that's a more formal definition. The next part here actually puts it into an equation. So the last notes we showed the CEO example, and now we've actually got a p-value for it. Apparently, the p-value is 0.008. Okay, without even knowing anything about p-values, you know 0.008. That's a really small probability. And we're sort of taking it slow here in the sense that we haven't even talked about how to calculate these yet. And we will. We'll get to that. We'll calculate the p-values. But the most important part is that you understand what it means, basically the definition of it, and how to interpret it. So what is it? Where does it come from? How do we interpret it? We haven't even talked about how to calculate it yet. We're not there yet. One thing I want to point out, I really don't like the 2 out of 12 in this case necessarily, because people just get their numbers mixed up and they look at 0.12 and they see 2 out of 12. So 2 out of 12 is a decimal. I'm going to rewrite this statement for the CEOs. So it's a conditional probability, and instead of the 2 out of 12, let's just write the decimal 0.167 here. So if we think back to chapter 5 for a minute, this bar in the middle, that represents a conditional probability. This statement really says, what's the probability we would get a sample proportion of CEOs less than or equal to 12% if we assume the true population proportion is indeed 0.167? Well, apparently that's a really small answer, right? 0.008. So we've got this expression. We know it equals 0.008. Let's give it a shot and let's try to interpret that. And I want to start with the condition here. The condition being this guy at the end. So assuming that CEOs, their birthdays are actually fair, right? So one way you might say it, assuming the birthdays of CEOs are uniformly distributed, right? Meaning evenly distributed, in other words. Another way someone might say that, and I think we said it in the previous notes, we said the birthdays are fair, right? So June and July, they got 2 out of 12. So we are going to operate under that assumption that everything's fair. Basically, that the true proportion would be 0.167. How did we get that? We took 2 and we divided it by 12, right? So we're going to operate under that assumption that everything's fair. In doing so, okay, well, then what's the probability that we would actually get a sample proportion that low? Well, That's what that 0.008 answer represents. So we can say there's only a 0.008 probability of getting a sample proportion as small or smaller than 0.12, right? Because p-hat's our sample proportion. So there's only a 0.008 probability of getting a sample proportion as small or smaller than 0.12 by random chance alone. So that's really what that 0.008 number means in the context of this setting, right? And I want to look at that equation a little bit closer here. Because I have an iPad, I can just erase this junk and I can do whatever I want. So I'm going to rewrite it. So this conditional probability, got a capital P, got some parentheses, and then I got the bar in the middle. So I'm assuming, right, my condition that the true P is 0.167. Basically, I'm assuming that everything's fair. So we're operating under that assumption. Assuming CEOs' birthdays are fair, well, man, those statisticians, whoever ran the data, it looked like they got 12% for their sample proportion. That seems like it's pretty low. So we want to know what's the probability that we would actually get a sample proportion less than or equal to that 12% number, right? And we're going to assume that, in reality, that everything's fair. The true proportion is 0.167. So assuming the true P is 0.167, what's the probability of obtaining a sample proportion, which is our p-hat, of 0.12 or less? That's really what this is all about. Well, I told you you don't know how to calculate it yet, but it's already here for you. Right? The only important part is that you know how to interpret it. That's our p-value. The answer, it's already given to us in this case, would be 0.008. Right? I just wanted to take a closer look at this statement and what was going on here. So let's go ahead and take a look at the next example here. This one has to do with golf again. It says, when Mike was testing a new 7-iron, the hypotheses were, well, the null hypothesis was the true standard deviation is 15, which was in yards, versus the alternative, which suggested it was somehow less than 15, like it was a more consistent golf club, where sigma is the true standard deviation of the distances Mike hits golf balls using the new 7-iron. Based on a sample of shots with the new 7-iron, the standard deviation was, and that's little s with a subscript x, right? That's our sample standard deviation, was actually 13.9 yards. So Mike might start getting excited about that. But just because he hit a certain amount of shots and had this lower standard deviation, does that necessarily prove that this golf club is indeed better? So what are the two explanations for why we got a sample standard deviation, little s? It's the same thing as little s with a subscript of x there, being less than 15. Well, I guess it could have just been a random occurrence, right? That's one example. Could have just been a random occurrence. Or, that golf club truly is better, and its standard deviation went down like the alternative suggests. So let's align those thoughts with the hypotheses in this case. So our null hypothesis, sigma equals 15. The alternative, sigma is less than 15, suggests that this new club is better somehow. So the null is the one that says nothing's changed. Everything stays the same. It's still 15. Don't get all excited, Mike. So really the null is the one that's saying, yeah, it was probably just a chance variation, right? It suggests that the sample, 13.9, I know it's lower than 15, but that was just due to chance in this case, right? Don't get too excited. So the null says, nothing's really changed. The alternative says, wow, your sample standard deviation was 13.9. Man, whoever said it's truly 15 yards must be wrong. That sample of 13.9, right, that sample standard deviation, that's just too rare to have happened by random chance. We can't ignore that. So that's the argument that's made for the alternative. The great thing is that as statisticians, we're really only swayed by numbers. That's our argument. So suppose the p-value from this data is actually 0.28. Interpret that p-value in context. So the p-value is 0.28. Seems relatively high, right? To me, I'm seeing a 28% chance of something happening. Let's interpret that. And before I start here, let's see if we can make that a probability statement. So capital P, the probability that we get a standard deviation less than or equal to 13.9. That's really what we want to know. What's the probability that all of a sudden Mike comes out and he's really good at golf, and the standard deviation of all his shots, they're actually really a tight grouping. So what's the probability the standard deviation is less than or equal to 13.9, assuming the null was actually true, assuming the population standard deviation or the true standard deviation was 15 yards. Sounds like a lot of work. It actually isn't that much work. But in this case, we don't even have to do it. They've already given it to us. This is the p-value, right? Assuming the null is true, assuming the true standard deviation is 15 yards, what's the probability you would see something 13.9 or smaller in a sample standard deviation? And apparently, that's 0.28. So no math to be done. This is a really common question for this chapter. You're given the p-value, you just have to interpret it in the context of the setting. So we can always start with, well, assuming the null's true, right? So if the true standard deviation of Mike's shot is indeed 15 yards, and so we're starting with that null hypothesis thing. If we assume that's true, there's a 0.28 probability that the sample standard deviation would be 13.9 yards or less just by chance alone. So really you can take that approach every single time. This is a very common question. Here's a p-value, interpret it in context. You can just say, well, assuming that whoever made up that null hypothesis, assuming they're not lying, there's a blank probability that we would get sample data this extreme. At the bottom of the page here, what are the two possible conclusions for a significance test? And I want to relate this to a criminal trial. Seems like we're all pretty familiar with the two possible outcomes that a judge can bring down from a criminal trial. Right, so if you think about it, in a court of law, you can only be proven not guilty or guilty. Right, those are the only two possible verdicts. The judge will never come down and say, this person is absolutely, truly, 100% innocent, right? So you can either say not guilty or guilty, but you can't say innocent. So this is the same exact approach we take in stats, except we don't use the word guilty, right? So there's two different scenarios. If our p-value is really small, which I think 5% is usually a good cutoff, right? 0.05. If our p-value is really small, like less than 0.05, we can reject the null. So we can say, hey, look, this is too rare to have happened by chance. I can't ignore this evidence. I've got evidence in support of this alternative hypothesis. So if the p-value is small, we can reject the null hypothesis. Okay, so keeping with the criminal trial logic here, if the p-value is large, which means, let's say, bigger than 5%, right? Bigger than 0.05, you don't get to say innocent, right? If you rejected the null here, you don't get to say except, for example. That would be a no. But you can say, if it's guilty here, you could say not guilty here. So if reject is guilty, not guilty, we would say you fail to reject the null. For instance, in the last example, the p-value was 0.28, which is way above 5%, so we wouldn't have convincing evidence, right? That's not convincing enough evidence to support the alternative claim. So at the end of the day, we really can't rule out the null hypothesis being true. But we certainly never would say, oh, we accept the null as being true. We can either reject it or fail to reject it. Those are our only two options. Okay, what are some common errors that students make in their conclusions? So we do this whole state, plan, do, conclude problem, and you either reject or fail to reject. One thing kids forget to do is they leave out the context. You've got to use those words from the problem. Whether you're talking about golfing or having a fever, you've got to use those words from the problem. The other thing is they still, for some reason, try to accept the null hypothesis, right? That's like a judge saying someone's innocent instead of not guilty. That's wrong. So don't use the word accepting or accept when you're talking about the null hypothesis. You can only reject or fail to reject. Another one is not linking the conclusion, whether you reject or fail to reject, to the p-value. So if you just say, we reject the null. Okay, why? You have to say something about the p-value, because the p-value was either really small, so you rejected it, or it was too large, so you failed to reject it. So the p-value is what tells you whether you should reject or fail to reject. So make sure you mention it like as the reason you're making that conclusion. The next part here says, what is a significance level? When are the results of a study statistically significant? Again, we've actually been referring to this all year. A significance level determines what is too small for a p-value. And the notation we use is the Greek letter alpha, a little lowercase. Mine kind of looks like a fish. I'm not that great at drawing it. But this is alpha. So that's our significance level. And to be statistically significant, you would have to be really rare. You'd have to be below whatever the value of alpha is. So what are the typical alpha levels? Well, the one we've talked about all year is 5%, 0.05. In most cases, if your p-value is below 0.05, it's statistically significant, right? If that's the alpha level and you beat it, you're statistically significant. Or some people are less picky. They use 10%, 0.1 is their alpha level, okay? So anything below 0.1 for a p-value would be statistically significant in that case. And then other people, for whatever reason, are really picky, and they need their alpha level to be 0.01. So only a 1% chance, for example. So they need their p-value to be less than 0.01 to be statistically significant. So those are the three big ones. And I'd say 0.05 is the most common of those three. So I've made some room here. Let's go ahead and add that note. When are the results of a study statistically significant? Well, before we just said when they're too rare to have happened by chance. Well, now we know that means when our p-value ends up being below whatever the alpha significance level is. And depends on who's really picky, whoever made the alpha significance level. But if our p-value is below that, wow, our results must be statistically significant. And that means we would reject the null hypothesis. So let's put that to use here in the CHIPS example. It says, for a second semester project in AP Statistics, Xenon decided to investigate whether students at his school prefer name brand potato chips to generic brand potato chips. After collecting data, Xenon performed a significance test using the hypotheses the null is P equals 0.5, so 50-50, versus the alternative, P is greater than 0.5, where P was the true proportion of students at his school who actually prefer the name brand potato chips. The resulting p-value was 0.074. By the way, I think that was really smart for the null hypothesis to be 50-50, right? So true p is 0.5. So no difference between the two. And then the alternative suggests that maybe the majority of the kids at his school are actually in favor of the name brand chips. So we've got the p-value. It's 0.074, or about a 7.4% chance. So what conclusion would you make given the two different scenarios, right? And you'll notice 7.4% is between these two alpha levels. So we're going to make a different decision at each one. So for part A, what if the alpha level was 0.1? Well, looks like our p-value actually beats that, right? Our p-value is actually below that. So because the p-value of 0.074 is less than alpha equals 0.1, we'd reject the null, right? We'd reject the null hypothesis. So our p-value is less than alpha, right? 0.074 is definitely less than 0.1, so we would have to reject the null in this case. In other words, for part A, this scenario, the results would be statistically significant. So what does that mean if we reject the null? Well, that means we would have convincing evidence that the students at the school actually prefer, or at least a majority prefer, the name brand potato chips. So if we reject the null, we have evidence that supports the alternative. So that's that context piece that you'll need in your conclusions. The math is all great, and this is the right decision to make. But to get full credit, you have to say what that really means in context. That means you've got convincing evidence that the students at the school are actually in favor of the name brand potato chips. Okay, but for someone that's more picky, the scenario for part B, what if the alpha was 0.05? Well, you probably noticed that 0.074 is bigger than 0.05. So that's going to change our decision. So if we use 0.05 for the alpha, we'd say, well, our p-value, it's actually greater than 0.05. So if you use that alpha, we'd have to fail to reject the null, right? So if the p-value is actually greater than alpha, you didn't get below it, it's not rare enough to say it's statistically significant. So we would fail to reject the null. So in context, that means we wouldn't have convincing evidence that the students actually prefer name brand over the generic, right? It could still be 50-50. We don't have enough convincing evidence to say otherwise. So notice that's just two different scenarios for the alpha level. The first one, we rejected the null because the p-value was less than alpha. Second one, we couldn't reject the null, right? We failed to reject because our p-value was actually greater than the alpha significance level here. All right, so the last piece here, just from that last example, it almost seems kind of arbitrary. Whoever picks the significance level, like what should it really be set at? Well, it can depend on a couple factors. One, how plausible is the null hypothesis? Is it a ridiculous claim? Is it something that's really practical? I don't know. So that's something to consider. How plausible is the null hypothesis in reality? The other thing is, what are the consequences if you reject it or you fail to reject it? Either way, what are the consequences? So just a couple things to consider if you're the one that has to define it. And one thing I want to point out is that both of those are somewhat subjective. For better or worse, most of the problems we do in AP Stats alpha, the significance level, alpha, is typically already given to us in the problem. And if not, we feel pretty comfortable just using 0.05. All right, we've talked about p-values and all that they are. We haven't even calculated them yet, but most importantly, we have to be able to interpret them. And we talked about the conclusions that we could make based on our p-value as it compares to the alpha significance level. That is enough for these notes, so I will see you in class.